Hey, what's up everybody? In this video I'm going to talk about how to find chemical formulas for compounds. And this instrument that you're looking at right here, this is called a CHN analyzer. And what this thing does is it determines the elemental composition of a sample. And as you've probably already figured out by now, the three main elements that this instrument analyzes are carbon, hydrogen, and nitrogen. So remember, in my last video I talked about how to find the mass percent composition of an element in a compound just given the chemical formula of that compound. But what if we wanted to do the opposite? In other words, what if we wanted to find the chemical formula of a compound only given the relative masses of that compound's constituent elements? Could we do that? And the answer is yes, we can. However, the formula that we can find is an empirical formula, not a molecular formula. So I think right now would be a good time to revisit the difference between empirical and molecular formulas. So remember, the empirical formula, that's the formula that only shows you the relative numbers of atoms of each element. The molecular formula shows you more. It shows you the absolute numbers of atoms of each element. And remember that the molecular formula is always a whole number multiple of the empirical formula. And that's going to be very important, especially later on when we actually try to find the molecular formula for a compound. So to demonstrate this a little bit, suppose our empirical formula, suppose that was, let's say, NO2. So if we have an empirical formula for NO2, then that means our molecular formula, it could also be NO2, or it could be N2O4, and so on and so forth. It could be NO2 multiplied by any whole number. So that's what I mean when I say that the molecular formula is always a whole number multiple of the empirical formula. So let's save that for later. So let's go ahead and do an example where we calculate the empirical formula of a compound given the masses of the two elements in that compound. So this example says that the decomposition of a sample of ethylene produced 81.673 grams of carbon and 13.708 grams of hydrogen. Calculate the empirical formula of ethylene. So again, we start out with the relative masses of carbon and hydrogen in this sample of ethylene, and we're asked to calculate the empirical formula. And remember that chemical formulas don't show you the relationship between masses. They show you the relationships between the number of atoms or the number of moles of atoms. So what I'm going to do is I'm going to take each of these two masses and I'm going to convert them to moles. So let's start with our carbon. So we have 81.673 grams of carbon, and I'm going to convert that to moles using the molar mass of carbon, which is given on the periodic table. The molar mass of carbon, I'm going to put the mass on the bottom, that's 12.0107 grams. That's what I'm going to put on the bottom, grams of carbon. I'm going to put my 1 mole of carbon on the top. And let's make sure units cancel. They do. Grams cancels with grams. And our answer here is going to be 6.8000, making sure we keep it to 5 sig figs, 6.8000 moles of carbon. So now we're going to do the same thing with hydrogen. We have our 13.708 grams of hydrogen. And we're going to use the molar mass of hydrogen to convert from grams to moles. So that's going to be 1.00794. Again, this is from the periodic table. Grams of hydrogen per 1 mole of hydrogen. As always, we're going to cancel out our units. Grams cancels with grams. And our answer is 13.600 moles of hydrogen. So what we've just done is we've determined the moles now, or the amounts, instead of the relative masses. Now we have the relative amounts of carbon and hydrogen in our sample. So what I'm going to do is I'm going to write what's called a pseudo formula, where I'm going to just do this. I'm going to put C6.8. This isn't our actual formula. This is what we call a pseudo formula, and this is going to help us actually get our real empirical formula. So we have C6.8 H 13.6. So now all we have to do here is we have to find the greatest common factor of these two numbers so that we can find the chemical formula. So to find the greatest common factor of two numbers, what you do is it's basically like a trial and error process. You start by dividing by the smallest value, and if that doesn't give you whole number multiples, in other words, if that smallest value doesn't divide evenly into all of your values, then you would move on to half of the smallest value. If that didn't work, you would move on to a third of the smallest value, then a fourth of the smallest value, and so on and so forth until you actually found a number that could divide, that all of your numbers are divisible by. So what we're going to do is we're going to start with our smallest value, and that's that 6.8. So we're going to divide both of these numbers by 6.8. 6.8 divided by itself, that's going to be 1. So our formula is CH something. We're going to leave that carbon alone because there's an understood 1 under there, even though we don't show it. And 13.6 divided by 6.8 is 2. So in this case, dividing by the smallest value was enough. We didn't have to go any further. And our empirical formula in this case is CH2. Again, that's not our molecular formula, that's just our empirical formula. That means that our molecular formula could be CH2, it could be C2H4, it could be C3H6, it doesn't matter. But this is what our empirical formula is, and if you wanted to calculate the molecular formula, you would need some more information, and we're going to do that in another example. So let's go ahead and talk about finding the molecular formula for a compound. Well, to find the molecular formula for a compound, you need two key pieces of information. First of all, you need the empirical formula for the compound, and then you also need the molar mass of the compound. So how do you calculate the molecular formula of a compound given these two pieces of information? Well, we established earlier that, again, the molecular formula, we said, is a whole number multiple of the empirical formula. So in the form of an equation, it sort of looks like this. Molecular formula equals empirical formula times n, where n is equal to 1, 2, or 3, etc. So if this is true, then this must also mean that the molar mass of your compound is also a whole number multiple of the molar mass of your empirical formula. So the molar mass of your compound is going to be the molar mass of your empirical formula times that same number n. So to demonstrate this further, I'd like to bring your attention to two compounds, cyclohexane and ethylene. We actually talked about ethylene earlier. And the molecular formula for cyclohexane is C6H12, and it has a molar mass of 84.16 grams per mole. Ethylene, which we saw earlier, the molecular formula for ethylene is actually C2H4, and it has a molar mass of 28.05 grams per mole. Now, in both of these cases, the empirical formula is CH2, and the molar mass of just your empirical formula, in other words, the molar mass of 1 mole of carbon added to 2 moles of hydrogen, is 14.02 grams per mole. So let's see if we can't divide the molar masses of these two compounds by the molar mass of our empirical formula and see if we don't get some small whole numbers. So I'm going to start with ethylene. We'll take our molar mass of ethylene, 28.05 grams per mole, divided by our empirical formula molar mass, 14.02 grams per mole, and that gives us a solid 2. Let's do the same thing with cyclohexane, 84.16 grams per mole divided by that 14.02 grams per mole, and that gives us 6, which makes sense because if we take that CH2, multiply it by 6, we'll get C6H12. You see how that works? Not only is the molecular formula a whole number multiple of the empirical formula, but the molar mass of your compound is also a whole number multiple of your empirical formula molar mass. So with that in mind, let's see if we can't help algebraically clean this equation up a little bit. So again, the molar mass of your compound is equal to the molar mass of your empirical formula times n. So what I'm going to do here is I'm going to divide both sides of this equation by the molar mass of your empirical formula. In so doing, the right-hand side of your equation is going to be greatly simplified because these two terms will cancel, and then that's going to solve for n, and that means that n is equal to the molar mass of your compound divided by the molar mass of your empirical formula. Once you have n, all you have to do is multiply that by your empirical formula, and voila, that gives you the molecular formula. So that may have sounded like a mouthful, but as always, we're going to do an example to see what this looks like. Okay, so the example says that the empirical formula of adamantane is C5H8, and its molar mass is 136.23 grams per mole. And it says to find the molecular formula of adamantane. Okay, so what we're going to do is we're already given the molar mass of adamantane. All we have to do now is we have to find the molar mass of the empirical formula. So let's go ahead and do that. So again, we have 5 carbon atoms. And we're going to multiply that 5 by the molar mass of carbon, which is 12.0107 grams per mole. And we're going to add to that the amount of hydrogen atoms, which is 8, times the molar mass of hydrogen, which is 1.00794 grams per mole. And I'm just going to stick it in down here. The molar mass of our empirical formula is going to end up being 68.1170 grams per mole. So again, we have the molar mass of our compound of adamantane, that's given, and then we just calculated the molar mass of our empirical formula. So all we have to do is just divide one by the other. So our N in this case is going to be 136.23 grams per mole, divided by our empirical formula molar mass, which is 68.1170 grams per mole. Of course, the grams per mole are going to cancel, and it's just going to be a unitless number. And N ends up being 2. So now, again, all we have to do is multiply N by our empirical formula, and that's going to give us our molecular formula. So if we take 2 times our empirical formula, C5H8, that's going to give us a molecular formula of C10H16. So really all we had to do was just, use the periodic table, find out the molar mass of our empirical formula. Like I said, the molar mass of our compound was given already, and all we had to do was just a simple division problem to determine that multiple of the empirical formula, and then all we had to do is multiply that through, and that gives us our molecular formula. So it's pretty straightforward, and I hope this video was helpful to you guys in some way. And all right, stay tuned for more.